This is Mr. Craig, and I'm going to do example part 2. So I'm going to flip the page over here. And in example part 2, very similar to example number 1, we have 4 trials in this case here. And we have the reaction where we have nitrogen monoxide reacts with bromine to form NOBr. Again, we really don't care about the balanced equation, so we never want to get distracted by that. So let's start off with the rate law. So we know that the word rate would be nice if they would write it, is equal to the constant K, and we have our NO, and we don't know what the order is yet, so I'm going to leave that blank. And then bromine, and I don't know what the order for that is yet. So when we finish, we'll put in the orders on the top here. Alright, just like in the first example, pick 2 experiments. Ideally, we want to try to make the concentrations the same for one of the reactants first to start off with. So if you look at experiment 1 and experiment 3, the nitrogen monoxide has the same concentrations there, so it's a good one to start off with. So let's compare experiment 3 to experiment 1. And again, you don't have to start with this one, and would love for this thing to write. And in experiment 3, we deal with the rates first. So in experiment 3, we have 60 over 24. Ugh. 24, and 60 divided by 24, I believe, is 2.5. Okay? So what that is saying is that experiment 3 is 2.5 times faster than experiment 1, based on the concentrations that are given there. Alright, so let's find out what the order of one of these happens to be. So we go ahead and plug in the data from experiment 3. So again, K, and the concentration for the nitrite in experiment 3 is 0.1, and we don't know what the order is yet, so we'll determine that. And for the bromine, it's 0.5, and we don't know what that is either. All over. Really? Come on. I'm going to move that up a little bit. Maybe that's the problem. Also 0.1. Nope, that was not the problem. And in experiment 1, that is 0.2. Okay. So again, cross off anything that is the same. So the K's, really, come on. K's are the same, these are the same. So now we have 0.5 divided by 0.2. So again, that is 2.5 to the n power. So what that means is 2.5 to the n is equal to 2.5. Therefore, n is equal to 1. Write it, please. So the bromine is a first order reactant. Okay, so we got that one out of the way. Alright, so let's come up to the data and let's find where the bromine has 2 concentrations that are the same. Well, it looks like in experiment 1 and 2 or in 3 and 4. So it's your choice. You get the pick. Let's go with 2 and 1. So in experiment 2 over experiment 1, my rates, and again I want to look at my rates, it's a 150 over 24. Okay. And 150 divided by 24, I believe, is 6.25. So what that's saying is that experiment 2 is 6.25 times faster than experiment 1. Okay. So let's plug in our values there. So in experiment 2, we have concentration 0.25 and 0.2. 0.25, and we don't know what M is yet. And 0.2 and that is a first order reactant. And then in experiment 1, we have 0.1 and 0.2. 0.1 and 0.2. First order as well. So again, cancel out anything that's alike. So these guys are gone, K is gone, constant remains the same. So we have 0.25 over 0.1, which is 2.5 to the M. And so now we have our rate, which is 6 1/4, is equal, please be equal to 2.5. Come on. 5 to the M. So M is equal to what? Now, some of you are going to stumble on this and say to yourself, how in the world are we supposed to figure that out? Remember, your only options for order are 0, 1, and 2. So if you're not sure, get your calculator out and type it in. So if you do 2.5 to the 0, then that has to be 1. If you do 2.5 to the first power, then that has to be 2.5. If you do 2.5 to the second power, or squared, then we have our order that we're looking for. So M is a second order reactant. What are you doing? Hang on here, sorry guys. Come on. It's a second order reactant. So our rate law will look like this, where rate is equal to K times the concentration, what is that, NO? Yeah, NO and bromine. NO, which we just calculated, is second order, and the bromine is first order. So there's our rate law for this reaction. Now again, the question was wanting us to determine the value of the rate constant, so we have to calculate what K is. So again, let's rearrange these variables so that we have K all by itself. We're going to have NO squared over bromine to the first power is equal to K. And again, you get to pick which experiment you want to use. Does not matter. Again, K is going to be constant for all of these. So, which one did we use last time? 1? Yeah. Let's go with number 3. So number 3, the rate is 60. The rate is 60 molarity per second. And the nitrogen monoxide is 0.1. So 0.1 squared. So we must square that if it's second order. And then the concentration for the bromine is 0.5. And that also is molarity, but it is a first order reactant. So before we get a number here, let's find out what our unit is. So our unit, the molarity is going to cancel out. We have molarity squared and seconds on the bottom, so we're going to have 1 over molarity squared per second. I'm not sorry, or not per second, but molarity squared second. That's a dot there. And then let's type this in on our calculator. So 60. So that's, I think that's 12,000. So 1.2 times 10 to the 4. And there's our value for K. Not too difficult. I'm really hoping that this year, and again, when I made this video, it's in 2011. I'm hoping that this shows up on the AP exam. It's been a couple years since we've seen a kinetics problem like this, and we are overdue. So this would be a type of problem that you would find in either question number 2 or question number 3 on the calculator portion of the AP exam. I hope this video has helped.